So today in this video, let's see about introduction to VLSI fabrication. So what is VLSI? VLSI is abbreviated as very large scale integration, where it is a process of creating integrated circuits by combining thousands of millions of transistors into a single chip. This advanced fabrication technique has revolutionized the electronic industry, enabling the production of powerful and compact devices like smartphones, computers, and modem electronics. The VLSI fabrication process involves a complex series of steps from wafer preparation to packaging. They require precise control and cutting edge technologies. Here, let's see about semiconductor materials and wafer preparation. Silicon, the workhorse. Silicon is a predominant semiconductor used in VLSI fabrication. Due to its excellent electronic properties, abundance and well-established manufacturing process, it forms the backbone of modern integrated circuits. Next we have wafer fabrication. Silicon wafers are produced by growing high purity single crystal in dots and then slicing them into thin polished discs. The wafer size has steadily increased over time, enabling higher chip densities and economics of scale. Doping and epitaxy to create necessary P and N junctions and control the electrical properties. The silicon wafers undergo doping with impurities. Epitaxial growth techniques are also used to deposit thin, high quality semiconductor layers on the wafer surface. Next we have photolithography process. In this process, the first step is wafer preparation. The process begins with clean silicon wafer, which undergoes various cleaning steps to remove any impurities or contaminants. This ensures a pristine surface for the subsequent photolithography steps. Photoresistant coating, a thin layer of photosensitive material known as photoresistant. In this spin coated onto the wafer, the photoresist is carefully chosen based on the desired pattern and resolution requirements. Exposure and development. The coated wafer then exposed to specific wavelength of light through a photo mask which contains the desired circuit pattern. The exposed or unexposed photoresist is then selectively removed during the development process, creating the desired pattern on the wafer. Thin film deposition technique. Evaporation. Evaporation is the most common thin film deposition technique in VLSI fabrication. It involves heating a source material until it vaporizes, then considering the vapor onto the substrate from a thin film. This method allows the precise control over the film thickness and composition. Next we have sputtering. Sputtering is a physical vapor deposition process that uses energetic ions to dislodge the eject atoms from a target material. The ejected atoms then deposit material onto the substrate, forming a thin film. Sputtering provides excellent step coverage and can be used for a wide range of material. Then we have chemical vapor deposition (CVD). In CVD, gaseous precursor chemicals are introduced into a reaction chamber and decomposes or react on the substrate surface. Depositing a thin film, CVD can produce high quality conformal films with precise thickness and composition control, making it crucial for VLSI fabrication. Next we have etching and doping process. Chemical etching, selective removal of material using a wet chemical solution. Next we have plasma etching, anisotropic etching using chemically reactive ionized gases. Ion implementation, doping semiconductor material with high energy charged particles. Etching and doping process are critical steps in VLSI fabrication. Chemical and plasma etching techniques enable the precise patterning of materials on the water surface. Ion implementation is used to selectively introduce impurities into the semiconductor, creating the desired doping profiles for transistors and other devices. These processes must be carefully controlled to ensure the integrity of the integrated circuit structures and maintain high manufacturing yields. Next we have metallization and interconnect layers. Interconnect layers, multiple conductive layers typically made up of metals like copper or aluminium, are used to connect different components and devices on a VLSI chip. These interconnect layers are essential for signal routing and power distribution throughout the integrated circuit. Thin film deposition. The metallization process involves depositing thin film of conductive materials such as metals on the semiconductor wafer. Various deposition techniques including sputtering, vaporization and chemical vapor deposition are used to create these interconnect layers with precise thickness and composition. Patterning and etching. After the metal layer are deposited, they are patterned using photolithography and etched to form a desired interconnect structures. This allows for the creation of complex routing networks that connect different components and devices on the VLSI chip. Planarization and polishing techniques. First one, CMP, chemical mechanical polishing, which removes the excess material through combined chemical and mechanical action. Spin-on dielectric planarization deposits viscous dielectric layer that is then spun and hardened. Resist etchback planarization etches back a photoresist layer to create a flat surface. And VLSI chip designs become more complex with multiple interconnect layers. Planarization and polishing techniques play a critical role in ensuring a smooth and uniform surface for subsequent process steps. Chemical mechanical polishing is widely used method that combines chemical etching and mechanical abstraction to remove excess material and create a planar surface. Spin-on dielectric planarization coats the wafer with a viscous dielectric layer that is then spun and hardened, while resist etchback planarization selectively etches back a photoresist layer to achieve a flatter topography. Next we have packing and assembly. Advanced packing techniques. VLSI chips require integrate packing to protect the delicate circuitry and facilitate connections to the outside world. Advanced packing methods like ball, grid, array, BGA and flip chip provide high density interconnects and robust mechanical support to the chip. Automated assembly process. VLSI fabrication cumulates in the assembly of the packed chip onto the circuit board or module. Sophisticated robotic system carefully place and solder the chip using precise high speed automated processes to ensure reliability and consistency. Rigorous testing and validation. Before VLSI chip can be shipped, it undergoes extensive testing and validation to ensure it meets all performance and reliability requirements. This includes electrical testing, thermal cycling, and environmental stress screening to catch any defects or weaknesses. Yield and reliability considerations. Maintaining high yield and reliability is crucial in VLSI fabrication, as even minor defects can lead to significant losses and failures. Factors such as process control, clean room environment, and robust testing procedure are critical in ensuring consistent and reliable chip protection. Yield refers to the percentage of functional chips produced from the wafer, while reliability considers the long-term performance and lifespan of the devices. Advanced statistical process controls techniques, rigorous contamination monitoring, and comprehensive testing at various stages of fabrication process help maximize yield and ensure durability of VLSI chips. Additionally, design for testability and design for manufacturability principles are implemented to improve the overall fabrication process and reduce the likelihood of defects. By continuously optimizing and improving these considerations, semiconductor manufacturers can deliver high quality, reliable VLSI devices to the market. Future trends of VLSI fabrication. As semiconductor industry continues to push the boundaries of device scaling, the future of VLSI fabrication holds exciting advancements. Emerging technology like extreme ultraviolet lithography are poised to enable the creation of ever smaller transistor, allow the increased chip density and performance. Additionally, innovations in material sciences such as use of novel dielectrics and high mobility channel materials will enable the future device scaling and performance efficiency improvements. Parallel to these technological breakouts, the industry is also exploring alternative fabrication approaches, including 3D integration and chiplet based architecture to overcome the challenges of traditional 2D scaling. Beyond device scaling, the further future of VLSI fabrication also encompasses advancement in processor or process automation, optimization, and sustainability. The continued development of machine learning and artificial intelligence algorithms will enable smarter and more efficient manufacturing process, improving overall yield and reliability. Additionally, the industry is also placing a greater emphasis on reducing time, the environmental impact on semiconductor manufacturing through the adoption of more sustainable materials and energy efficient fabrication techniques. Thank you.